In this video, we're introducing Maclaurin series purely by example, and I'll just post a link to a more general derivation. So the idea of a Maclaurin series starts out with what seems like an insane proposition. And there it is. Suppose I told you that I want to express this transcendental function e to the x as a polynomial, allowing myself to possibly have infinitely many terms in it. It doesn't seem like it should be doable, but I immediately notice how to get the first coefficient out of it. If I evaluate this at x equals 0, I'm going to get a c0 out in front, and then every other term vanishes. So given that e to the 0 is just equal to 1, I've just figured out my first coefficient in my polynomial. And as odd as this proposal seems, that wasn't so hard, so I have hope that we can get this done. We just need to come up with a trick to expose the next constant. And what I notice is I could take the derivative of both sides of this thing. E to the x is particularly simple. It's equal to its own derivative. And then I differentiate every one of these terms, and I get a c1, and I get a 2c2x, 3c3x squared, and so on. And then I realize plugging in 0 works again to expose a coefficient. And I have c1 equals e to the 0, which is 1. Let's continue this process until we're able to detect some kind of pattern in the c's. There's our second derivative of e to the x. I evaluate that at x equals 0. And that exposes c2 while every other term vanishes. And now I have that 2c2 is equal to 1, which means c2 is just 1/2. Continuing the process, another derivative. The constant term dies. I get a 3 times 2 times c3 exposed out in front. And then I have a 4 times 3 times 2 times c4 times x plus other stuff with higher powers of x. I plug in x equals 0. And every term except the first is going to vanish. Again, e to the 0 is 1. So that's equal to 3 times 2 times c3. So c3 is 1 over 3 times 2. I'm starting to detect something that looks like factorials here. And I'm just going to take one more term just to really nail down what's going on. Another derivative is going to expose that constant c4. And then I'm going to have additional terms with x's in them. I plug in x equals 0, and all those terms with x's in them die. And I have only the one out in front. 4 times 3 times 2 times c4. That has to be equal to 1, or e to the 0. So my c4 is going to be 1 over 4 times 3 times 2. So now I've got the pattern. In the denominator there is just 4 factorial. And so I could write this as 1 over 4 factorial for c4. c3 is 1 over 3 factorial. c2 is 1 over 2 factorial. 2 is just the same thing as 2 factorial. And I can extend all the way back to the beginning. c1 is 1 over 1 factorial. It's just a fancy way of saying 1. And c0 is 1 over 0 factorial, remembering that 0 factorial is defined to be 1. So now I can state in general what Cn is. It's just 1 over n factorial. And it might be nice to write down e to the x in summation notation. The sum as n goes from 0 to infinity, and it's just all of these terms. And our Cn's are 1 over n factorial, and each one of those is stuck to an x to the n. So I end up with x to the n over n factorial. The last thing I want to do here, since we now have a power series representation of e to the x, is find the interval of convergence for it. In other words, the range of x values for which this series is convergent. And the standard approach to this is to use the ratio test. And this is how the ratio test goes. I look at the ratio of the n plus 1 term to the nth term with absolute value bars around it. If the limit of this thing as n goes to infinity turns out to be less than 1, then I know my series will converge. I plug in the n plus 1 term. Then I divide by the nth term, which is the same as multiplying by its reciprocal. Now I'm going to cancel n factors of x, leaving me with only one factor of x. And in the denominator, I'm going to split off an n plus 1 and write it as n plus 1 times n factorial. Now I see that my n factorials cancel. And I want to do something as I write down the next step. We have to realize that x is a constant with respect to the n limit. And so that absolute value of x can come out in front. The rest of this stuff is positive, so I can drop the absolute value bars. And that limit unambiguously goes to 0. The denominator is growing to infinity, the numerator is staying constant. So it doesn't matter what x is. That limit is 0, and therefore absolute value of x times that limit is also 0. And this is less than 1, no matter what x is. If I want to express that in terms of an interval of convergence, that interval is negative infinity to infinity. In other words, this power series converges for all real values of x. So there's our first Maclaurin series example. Again, we just proposed that a function could be written as a polynomial. We relied on the fact that our function was well behaved, so we could use a derivative trick to expose one coefficient after another. And that way we ended up building this power series, or an infinitely long polynomial, to represent a transcendental function. Finally, things turned out so well that this representation turns out to be valid for any value of x.